There is a machine that costs $380 million. It ships in 40 freight containers. It contains over 100,000 individual parts, and no country on Earth can build a copy of it. Not the United States, not China, not Russia, not anyone. And without this machine, every advanced chip on the planet stops being made. No new iPhones, no new AI models, no new missile guidance systems, no next generation anything. One company builds it. One. And most people have never heard its name. Before we get to the company, you need to understand what's actually at stake. Pick up your phone. Inside, it is a chip, a semiconductor. It's a small piece of silicon, roughly the size of your fingernail, packed with billions of microscopic switches called transistors. These transistors flip on and off to process every piece of information your device handles. Every app, every photo, every search, every message. Billions of switches, firing billions of times per second. The smaller you make those transistors, the more you can fit onto a single chip. The more you fit, the more powerful the chip becomes. And for the past 50 years, the entire technology industry has been in an arms race to shrink transistors down as far as physics will allow. Today, the most advanced chips hold over 100 billion transistors. Each one is just a few nanometers wide. A nanometer is 1/1000th of a meter. A human hair is about 80,000 nanometers thick. We are building structures that approach the scale of individual atoms. And here's the part most people never think about. Designing a chip that complex is incredibly hard, but actually manufacturing it, physically printing billions of atomic-scale circuits onto silicon, is the single hardest industrial process humanity has ever developed. That's why the biggest names in tech don't even attempt it. Apple doesn't manufacture its own chips, neither does Nvidia. Neither does AMD, Qualcomm, Google, Amazon, or Microsoft. They all design chips, they draw the blueprints, they architect the logic. But when it comes time to physically produce the chip, to turn a design into something real, they hand it off. Because the fabrication process requires machines that operate at the absolute bleeding edge of physics. And the most important of those machines, the one the entire industry depends on, is built by a single company in the south of the Netherlands. ASML. ASML is headquartered in Veldhoven, a quiet city most people couldn't find on a map. The company was founded in 1984 as a small joint venture between Philips and a Dutch semiconductor equipment maker. No consumer products, no brand recognition, no billionaire CEO on magazine covers. But today, ASML is one of the most valuable companies in Europe and one of the most strategically critical companies in the world. Because ASML builds the only machine on Earth capable of manufacturing the most advanced semiconductors. It's called an EUV lithography system. And to understand why it matters, you need to understand what lithography actually is. Lithography is the process of printing circuit patterns onto silicon. Think of it as a microscopic stencil. You project light through a detailed pattern, called a mask, and that light etches the circuit design onto the chip's surface. You do this over and over, layer by layer, building up the chip's full architecture. Billions of transistors wired together in exact arrangements, each one placed with nanometer precision. For decades, the industry used a type of light called deep ultraviolet, DUV. It worked well, but as transistors shrank below a certain size, DUV couldn't keep up. Its wavelength was too large to print the finest details. Imagine trying to sign your name with a thick marker. You can write, but you can't capture small, precise strokes. That was the wall DUV hit. The answer was a fundamentally different kind of light, extreme ultraviolet, EUV. EUV light has a wavelength of just 13.5 nanometers, over 14 times shorter than the deep ultraviolet light it replaced. At that wavelength, you can print features so small they would have been considered physically impossible 20 years ago. But here's the problem. Generating EUV light and controlling it with enough precision to print circuits is one of the hardest engineering problems ever solved. Here's what happens inside ASML's machine. A high-powered laser fires 50,000 pulses per second at tiny droplets of molten tin. Each droplet is hit twice. The first pulse flattens it. The second vaporizes it. When the tin vaporizes, it releases a burst of EUV light. That light is then captured and directed by a series of mirrors. not ordinary mirrors. These are the most precisely polished objects ever manufactured by human hands. If you scaled one of these mirrors to the size of Germany, the tallest imperfection on its surface would be less than a millimeter. That degree of perfection is non-negotiable because EUV light is absorbed by nearly everything. Glass absorbs it, air absorbs it. You cannot use lenses, only mirrors. And those mirrors must be essentially flawless. The light bounces through the mirror system, passes through the chip's design pattern, and projects that pattern onto a silicon wafer coated in light-sensitive material. Then the wafer shifts, the process repeats, and another layer of the chip is built, over and over until the chip is complete. One machine, the size of a double-decker bus, shipped across oceans in pieces, assembled on site by ASML engineers, costing more than a commercial airliner, and nothing else on the planet can do what it does. This is where the story gets serious. ASML has no competitor in EUV lithography, zero. Not Samsung, not Intel, not any Chinese state-backed enterprise, not any defense contractor on Earth. Others have tried, governments have funded attempts, billions have been spent, but the physics alone took over 20 years to crack. The engineering required deep partnerships across multiple countries, precision optics from Germany, light source technology from the United States, advanced manufacturing from the Netherlands. It wasn't one breakthrough, it was thousands, stacked on top of each other over 3 decades. This isn't a market where a startup can raise a few billion and compete. This isn't a problem a government can solve by throwing money at it for 5 years. The barriers aren't legal, they aren't patents, they're physics, precision, and 30 years of compounding institutional knowledge that no one else has. ASML holds a 100% market share in EUV lithography, 100%. Every advanced chip on Earth, built by TSMC in Taiwan, Samsung in South Korea, or Intel in the United States, was manufactured using an ASML machine, every single one. That means every AI model trained on cutting-edge hardware ran on chips made by ASML's light. Every advanced fighter jet, every flagship smartphone, every hyperscale cloud data center. All of it traces back to one company in one small Dutch city, building one machine that no one else can replicate. This isn't just a business advantage, this is structural dominance. The kind that doesn't erode with time, because the complexity required to compete is so extreme that competition cannot form. The machine is too intricate, the supply chain is too fragmented, the physics is too hard. ASML didn't crush its rivals, it solved a problem no one else could, and now the entire modern world, its economy, its military balance, its technological future, depends on that single capability continuing without interruption. If ASML stopped shipping tomorrow, the future would stall. To understand how one company ended up with this much leverage, you need to understand how the chip industry actually works, because it doesn't work the way most people assume. Most people hear NVIDIA and think NVIDIA makes chips. They hear Apple Silicon and think Apple runs a fab. They see AMD on a graphics card and assume AMD manufactured it. None of that is true. What actually happened is the chip industry split in two, and that split is the reason ASML's position is so dangerous. Decades ago, chip companies did everything in-house. Intel designed its own chips and manufactured them in its own factories. So did IBM. So did Motorola. Design and fabrication lived under one roof. But manufacturing chips kept getting harder and more expensive. Every new generation of transistors required more advanced equipment, cleaner facilities, tighter precision. Building a cutting-edge chip factory, called a fab, went from costing hundreds of millions to costing billions. Then tens of billions. Eventually, most companies couldn't justify the cost. Why spend $20 billion building a fab when you could spend a fraction of that designing a chip and paying someone else to manufacture it? So the industry split. On one side, you got the designers, companies called fabless because they own no fabrication plants. NVIDIA, AMD, Qualcomm, Apple, Broadcom, Amazon, Google. They design the chip, they architect the logic, they own the intellectual property, but they don't build anything physical. On the other side, you got the foundries, companies whose entire business is manufacturing chips that other companies designed. They own the fabs, they run the machines, they handle the physics. And the biggest foundry in the world, by a wide margin, is TSMC, Taiwan Semiconductor Manufacturing Company. TSMC is based in Hsinchu, Taiwan. It was founded in 1987 by Morris Chang, a semiconductor veteran who saw the split coming before almost anyone else. His pitch was simple: we will manufacture chips for anyone, and we will compete with no one. We won't design our own products. We'll just build yours, better than you could build them yourself. It worked spectacularly. Today, TSMC manufactures roughly 90% of the world's most advanced chips. When Apple unveils a new processor, TSMC built it. When NVIDIA releases its latest GPU powering AI systems around the world, TSMC fabricated it. When AMD, Qualcomm, or MediaTek announce new mobile or server chips, TSMC made them real. TSMC is the factory floor of the modern world, but TSMC doesn't build its own equipment. The machines inside TSMC's fabs, the lithography systems that print the circuits layer by layer onto silicon, those are ASMLs. Follow the chain. NVIDIA designs a chip. TSMC manufactures it. TSMC uses ASML's machine to do the manufacturing. Remove ASML and TSMC can't produce advanced chips. If TSMC can't produce, NVIDIA has no product. Apple has no processor. AMD has no GPU. Amazon and Google have no custom AI accelerators. The entire downstream collapses. ASML doesn't make chips. It makes the machine that makes the chips. And that position, one layer removed from the end product, is exactly what makes it so easy to overlook and so impossible to replace. Now, a reasonable question. Why can't someone else just build a competing machine? The answer is that EUV lithography isn't a single technology. It's a convergence of thousands of technologies, pulled together from across the globe, refined over 3 decades, and integrated into one system so complex that no single entity could recreate it alone. Start with the light source. The laser system that fires at molten tin droplets 50,000 times per second was developed by a company called Cymer, based in San Diego. ASML didn't invent it in-house. It acquired Cymer in 2013 for $3.7 billion, folding that capability directly into its supply chain. That laser technology alone took over a decade to develop to production-grade reliability. Then the mirrors. The reflective optics inside an EUV system are built by Carl Zeiss SMT, a German company with a precision optics pedigree stretching back over a century. These mirrors are polished to a smoothness measured in fractions of a nanometer. Zeiss doesn't sell these optics to anyone else for this purpose. It's a captive supplier. Its EUV mirror business exists essentially to serve ASML. Then the reticle stage, the wafer stage, the vacuum systems, the contamination control, the alignment sensors, the software that coordinates all of it in real time. Each one is a standalone engineering marvel. Together, they form a system with over 100,000 components, sourced from hundreds of specialized suppliers across Europe, the United States, and Asia. No single company controls all of these capabilities, but ASML is the only company that can integrate them into a working machine. This is why replication is functionally impossible on any short timeline. It's not one breakthrough you need, it's thousands, in optics, in laser physics, in materials science, in precision mechanics, in software, all of which have to work together inside a machine that operates at tolerances no other industrial system on Earth demands. This is not monopoly through aggression. This is monopoly through complexity. And now governments have noticed. In 2019, the United States government began pressuring the Dutch government to block ASML from selling its most advanced EUV machines to China. Think about what that means for a moment. The US didn't sanction a Chinese company. It didn't block a Chinese product. It went to a European ally and said, "Do not let this Dutch company ship its machine to China." Why? Because whoever controls chip manufacturing controls the future. Advanced semiconductors are not just consumer products. They are the foundation of artificial intelligence. They power military systems, autonomous drones, hypersonic missile guidance, electronic warfare, cyber offense. They drive surveillance infrastructure. They enable quantum computing research. They underpin economic competitiveness at every level. If China could manufacture its own cutting-edge chips, it wouldn't need to buy them. It could build its own AI infrastructure, its own military hardware, its own tech ecosystem, independent of Western supply chains. That possibility terrified Washington. So the US didn't just target chips, it targeted the machine that makes the chips. It targeted ASML. The Dutch government ultimately agreed. Export restrictions were imposed. ASML was barred from shipping its most advanced EUV systems to Chinese customers. Later, those restrictions were tightened further to include some of ASML's older but still highly capable DUV machines. In effect, the Western world decided that one company's shipping manifest was a matter of national security. Not because ASML is a weapons manufacturer, not because it builds military hardware, but because the machine it builds is the bottleneck through which all advanced technology must pass. ASML doesn't dominate headlines, it dominates capability. Zoom out. Forget ASML for a moment. Forget the machine, the mirrors, the tin droplets. Look at the map. The world's most advanced chips are designed in the United States. They are manufactured in Taiwan. And the machine that makes manufacturing possible is built in the Netherlands, using optics from Germany and laser technology from California. No single country controls the full chain. And that's not an accident. It's the result of decades of specialization, where each player became so good at one piece of the process that no one else could catch up. But it also means the entire system is fragile. Pull one piece out, and the whole thing buckles. Start with Taiwan. TSMC fabricates roughly 90% of the world's most advanced semiconductors. That means the vast majority of cutting-edge chips, the ones inside AI servers, advanced military systems, and next-generation consumer devices, are physically produced on a single island, 100 miles off the coast of mainland China, an island that China considers its own territory. This is not a hypothetical risk. The Taiwan Strait is one of the most heavily monitored and militarily contested waterways on the planet. The Chinese military conducts regular exercises simulating operations around Taiwan. U.S. naval assets patrol the region continuously. Diplomatic tensions between Beijing and Washington over Taiwan's status have escalated repeatedly over the past decade. If a conflict disrupted TSMC's operations, even temporarily, the global supply of advanced chips would collapse. Not slow down, collapse. There is no backup, no secondary supplier operating at TSMC's level. Samsung fabricates some advanced chips in South Korea, and Intel is building new capacity in the United States. But neither is close to matching TSMC's volume or consistency at the leading edge. The world's most critical manufacturing capability sits in one of the world's most geopolitically volatile locations, and everyone in power knows it. This is why the CHIPS Act exists. In 2022, the United States passed the CHIPS and Science Act, a $52 billion federal investment designed to bring advanced semiconductor manufacturing back onto American soil. The logic was straightforward. The U.S. designs the world's most important chips, but builds almost none of them domestically. That dependency is a national security liability. The CHIPS Act funds new fabs. TSMC is building plants in Arizona. Samsung is expanding in Texas. Intel is investing heavily in Ohio and Arizona. The goal is to reduce America's reliance on a single island in the Pacific for the chips that power its economy and its military. But here's what the CHIPS Act can't solve. You can build a fab in Arizona. You can pour $20 billion into the building, the clean rooms, the infrastructure. But inside that fab, you still need ASML's machine. There is no American alternative. There is no alternative, period. Reshoring chip manufacturing doesn't eliminate choke point. It moves the fab closer to home, but the dependency on ASML remains fully intact. Every new fab, built anywhere in the world, Arizona, Dresden, Kumamoto, still places an order with Veldhoven. The CHIPS Act addresses geography. It doesn't address the bottleneck. China understands this better than anyone. For years, Beijing has been investing aggressively in domestic semiconductor capability. Billions of dollars have flowed into Chinese chip companies, equipment makers, and research institutions. The stated goal is self-sufficiency, the ability to design and manufacture advanced chips without relying on Western technology. But EUV has proven to be a wall that money alone can't scale. Chinese companies have made progress in older chip manufacturing, the kind that uses DUV lithography and produces chips for cars, appliances, and industrial equipment. That's real, and it matters. But at the leading edge, the 5-nanometer and 3-nanometer nodes where AI and advanced computing live, China remains locked out. Without access to ASML's EUV machines, Chinese fabs cannot print the smallest, most powerful transistors. And without those transistors, they cannot produce chips that compete with what TSMC, Samsung, and Intel are building. Some analysts estimate China is a decade or more behind in developing a domestic EUV capability. Others say it may never get there independently. Not because Chinese engineers lack talent, they don't, but because EUV isn't a single problem to solve. It's an ecosystem: optics, lasers, materials, precision mechanics, software, integration, each one a mountain, and all of them must be climbed simultaneously. The export restrictions on ASML have made this even harder. China can't buy the machine. It can't reverse engineer a machine it doesn't have, and it can't easily replicate a supply chain that spans 3 continents and 30 years of institutional learning. This is the leverage. Not theoretical, not speculative, structural. And it raises a question most people haven't considered. What happens when one company is so embedded in the global order that it becomes a single point of failure? ASML's factory in Veldhoven is the origin point for every EUV system on Earth. If that facility were disrupted by a natural disaster, a fire, a cyber attack, a war, the production of advanced chips worldwide would grind to a halt, not immediately. Fabs have some inventory of existing machines and spare parts, but new capacity would stop. Expansion plans would freeze. The technological progress of the entire world would stall until ASML recovered. There is no contingency for that, no backup supplier, no emergency reserve of EUV machines sitting in a government warehouse somewhere. The machine is too complex to stockpile and too singular to source from anyone else. This is not a risk the market has priced. It's a risk most people don't even know exists. We've spent a century thinking about power in terms of oil. Who controls the oil fields? Who controls the shipping lanes? Who controls the refineries? Wars have been fought over it. Alliances have been built around it. Entire geopolitical frameworks rest on the assumption that energy is the resource that shapes the global order. That assumption is becoming outdated. The resource that now matters most is compute. The ability to process information at scale, the ability to train AI models, the ability to run autonomous systems, crack encryption, simulate physics, model economies, guide weapons. And compute requires chips. Advanced chips require EUV lithography, and EUV lithography requires ASML. The chain is that short and that fragile. Modern power is not about oil, it's about manufacturing precision at atomic scale, and that precision flows through one company in one small European city, building one machine that no one else on Earth can replicate. There's no dramatic conclusion here, no prediction of collapse, no warning of war. Just a structural reality that most people walk past every day without noticing. The most important company in the world doesn't sell to consumers. It doesn't run ads. It doesn't compete for your attention. It builds a machine that makes the future physically possible. And everyone else, every government, every corporation, every military, is waiting in line.